Hello viewers, today in this program I will explain some important theorems of vector calculus. Namely, I will explain Green's theorem, then Stokes theorem and then Gauss divergence theorem. These are three very important theorems of vector calculus. In the previous lecture, I have explained about line integration, surface integration and volume integration. I think you have the knowledge of line integration, surface integration and volume integration, which help you to understand the Green's theorem, Stokes theorem and Gauss theorem. I will explain first of all Green's theorem. Green's theorem, named after George Green 1793 to 1841, an English mathematician, is an important theorem in integral calculus. Using this theorem, certain line integral may be evaluated by converting them into double integral over plane surface and vice versa. That is, the double integral can be evaluated using line integral. The Green theorem is stated as: if R is closed region in xy plane bounded by simply closed curve C, and if phi xy and psi xy are continuous function and having continuous partial derivatives in the region R, then the integral over C phi dx plus psi dy is equal to double integral over the surface R del psi over del x minus del phi over del y dx dy. I will explain the proof of this theorem as follows. The proof of the theorem: since C is closed curve, two lines parallel to y axis can always be found such that C lines between the two lines, let x is equal to a and x is equal to b, be two such lines meeting the curve C at P and R respectively as shown in the figure. Let C1 y is equal to y1 x be the curve and C2 y is equal to y2 x be the curve R as P. Figure A shows the Green's theorem for the integration along a closed curve. Assume that y1 x is less than equal to y2 x, then C is equal to C1 plus C2, and we have integral over R del psi over del x minus del phi over del y dx dy is equal to integral from a to b, then integral from y1 to y2 del phi over del y dy dx, that is equal to integral a to b phi from y1 to y2 dx, that is equal to phi xy minus phi xy at the point y is equal to y2 and y is equal to y1. This is equal to minus of integral over C2 phi xy dx minus integral over C2 phi xy dx. Therefore, the integral over R, the region R, becomes minus of integral over C phi xy dx. Considering that the region R is bounded by the curve y is equal to C, x is equal to x1, y is equal to d, x is equal to x2. It can similarly be proved that integral over R del phi over del x dx dy is equal to integral over C phi xy dy. Subtracting these equations, we have the result as the double integral over the surface R del psi over del x minus del phi over del y dx dy is equal to the line integral phi dx plus psi dy, which proves the theorem. I will explain the example of use of Green's theorem. Use Green's theorem to evaluate a line integral e to the power minus x sin y dx plus e to the power minus x cos y dy, where C is the rectangle with vertices 0 0, pi 0, pi, pi by 2 and 0 pi by 2, that is the rectangle in first quadrant. Here the path of integration C of the given integral is closed curve bounded by the four sides of the rectangle joining the points 0 0, pi 0, pi, pi by 2 and 0 pi by 2. Let R be the plane region bounded by C. Then by the Green's theorem, the integral over C of the given integrand is equal to the double integral over the R del phi over del x minus del psi over del y dx dy, that is integral over C e to the power minus x sin y dx plus e to the power minus x cos y dy becomes double integral over the surface R del over del x of e to the power minus x cos y minus del over del y of e to the power minus x sin y dx dy, that is equal to the limit of integration here are x is equal to 0 to pi and y is equal to 0 to pi by 2 as the sides of the rectangles. Therefore, this integral becomes integral from x is equal to 0 to pi, integral from y is equal to pi by 2, then integrand here is e to the power minus x cos y minus e to the power minus x cos y dx dy, that is twice of integral from 0 to pi e to the power minus x dx, integral from 0 to pi by 2 cos y dy, that is equal to twice of e to the power minus x from 0 to pi and sin y from 0 to pi by 2, that is equal to twice e to the power minus x minus 1. Now I will explain you another theorem of vector calculus, namely it is Stokes theorem. Stokes theorem establishes under certain condition a relationship between a line integral over a simple closed curve and a surface integral over a surface, curved or plane surface, whose boundary is closed curve. This relationship sometimes help in evaluating a line integral by converting it into surface integral or the surface integral after converting it into line integral. This theorem was named after Irish mathematician Sir George Gabriel Stokes in 1819 to 1903. It is discussed as follow. The statement of the theorem is: if an open two-sided surface bounded by the simple closed curve C and f is any vector point function having continuous derivatives, then the line integral f dot dr is equal to the surface integral of curl of f dot ds, or the double integral over the surface as curl f dot n cap ds, where n cap is outward going normal vector of the surface. Proof of the theorem is as follows. Let f is function vector point function is defined as f1 I plus f2 j plus f3 k, and dr is equal to I dx plus j dy plus k dz. N cap here is cos alpha I plus cos beta j plus cos gamma k, where alpha, beta, gamma are the cos alpha, cos beta, cos gamma are the direction cosines of the vector function n cap. Here the integral over C f dot dr becomes integral over C f1 dx plus f2 dy plus f3 dz, and integral over C del cross f dot n cap is equal to integral over the surface S del f3 over del y minus del f2 over del z cos alpha plus del f1 over del z minus del f3 over del x cos beta plus del f2 over del x minus del f1 over del y cos gamma ds. This surface integral becomes the integration over the surface S del f1 over del z cos beta minus del f1 over del y cos gamma plus del f2 over del x cos gamma minus del f2 over del z cos alpha plus del f3 over del y cos alpha minus del f3 over del x cos beta over the surface S. Thus, we have to prove that the double integral over the surface S becomes the single integral, the line integral of the f dot dr as integral over C f1 dx plus f2 dy plus f3 dz is equal to the surface integral of curl f dot n cap ds. Now, I will explain the example for Stokes theorem. Consider a function f x y z is equal to 3 y I plus 2 j plus 3 x k. Then the line integral over the C f dot dr is equal to the surface integral of the curl f dot n cap ds. It is the Stokes theorem. Here the function is defined in a plane x is equal to 0, y is equal to 0, z is equal to 0, and the plane 2x plus 2y plus z is equal to 4. This forms a tetrahedron. Let us suppose this function is defined in the tetrahedron and we take the projection of the plane on xy plane, that is z is equal to 0 plane. Therefore, n cap becomes positive direction of z axis, that is n cap is equal to k. Now, we will find the curl of the given function. The curl of the given function is defined as the integral value in which first row is I j k, second row is delta over delta x, delta over delta y, delta over delta z, and third row represented by the coefficients of the I j k in the given function, that is 3 y, 2 z and 3 x respectively. So, the value of the curl f becomes minus 2 I minus 3 k, and n cap here is k. Therefore, the dot product of curl f and n cap, that is curl f dot n cap, becomes only minus 3. Therefore, the line integral over the curve f dot dr becomes the surface integral of minus 3 over the surface. Here this represents minus 3 s, where s is the surface area of the projection of the plane on xy plane. That area is equal to the area of this triangle of the side 2 and 2 on x and y axis. Therefore, its area is again half of base into height, that is equal to 2. To complete, therefore, the value of the complete integral is equal to minus 6. Now I will explain you the third important theorem of vector calculus, the Gauss divergence theorem. Gauss divergence theorem, named after the German mathematician called Friedrich Gauss in 1777 to 1855, states that the outward flux of a vector field across a closed surface is equal to triple integral of the closed surface. It thus helps in evaluating certain integrals over the space enclosed by the corresponding closed surface and is one of the most useful tool for the studies of electricity, magnetism, fluid flow, etc. The Gauss divergence theorem is stated as follows. The Gauss divergence theorem: if S is a closed surface such that any line parallel to the coordinate axis cuts S at most 2 points, and F is continuously differentiable vector point function in the region R bounded by the surface S, then the integral over the surface S f dot n ds becomes the integral over the volume V divergence of f dV. Here n is unit positive outward normal vector to the surface at any point. Proof of the theorem is as follows. Let us divide the closed surface S into an upper portion S1 and a lower portion S2 such that their projections on xy plane are the same. Say R, let z is equal to f1 xy and z2 is equal to f2 xy be the equations of S1 and S2 surfaces respectively. Consider any point P x y z within the region V as shown in the figure and a volume element dx dy dz at P. A divergence theorem, relation between the surface and volume integral as shown in the figure. Let the line through P parallel to z axis cut the surface S1 and S2 at the point P1 x1 y z and P2 x y z respectively. If f is a function defined as f1i plus f2j plus f3k, then divergence of f dv is evaluated as the triple integral over the V del f1 over del x plus del f2 over del y plus del f3 over del z dx dy dz. Therefore, the integral over V divergence f dv becomes the triple integral over V del f1 over del x dx dy dz plus triple integral over V del f2 over del y dx dy dz plus triple integral over V del f3 over del z dx dy dz, and hence the triple integral over V del f3 over del x dx dy dz becomes the double integral over R f3 minus f3 at f2 minus f3 xy f1, and similarly other two integral can be evaluated, and hence the triple integral over the volume V del f upon del z becomes double integral over the surface divergence of n cap ds. I will explain the example representing the Gauss divergence theorem. Find the outward flux of the function f is equal to log x square plus y square I minus 2z upon x tan inverse y by x j plus z root x square plus y square k across the boundary of the thick wall cylindrical region V is equal to, it is 1 less than equal to x square plus y square less than equal to 2, that is the cylinder having inner radii 1 and outer radii 2 in the plane z is equal to 0 and z is equal to 2. If S be the surface of thick walled cylindrical region V, the outward flux is given by double integral over the surface S f dot n ds. By the divergence theorem, double integral over the surface S f dot n ds becomes triple integral over the volume V bounded by the surface, and integrand here is divergence f dV. Now, divergence f here is equal to del over del x of log x square plus y square plus del over del y of 2z upon x tan inverse y by x and plus del over del z of z root x square plus y square. We evaluate the divergence here and simplify, it becomes 2x upon x square plus y square minus 2z upon x square plus y square plus under root x square plus y square. Thus, the triple integral over the volume V of divergence f dV becomes triple integral over the volume V of the integrand 2x upon x square plus y square minus 2z upon x square plus y square plus under root x square plus y square dV. Converting the cylindrical coordinate, this is given in the Cartesian form. So, we convert the system in cylindrical polar coordinate with x is equal to r cos theta, y is equal to r sin theta, z is equal to z. So, it becomes the integrand 2x upon x square plus y square minus 2z upon x square plus y square plus under root x square plus y square becomes 2r cos theta upon r square minus 2z upon r square plus r, and the cylindrical coordinates, the given thick walled cylinder region can be expressed as 1 less than equal to r less than equal to root 2, theta is in between 0 and 2 pi and z is in between 0 and 2. Hence, the flux is equal to the integral theta is equal to 0 to 2 pi, integral r is equal to 1 to root 2 and integral z is equal to 0 to 2 for the integrand 2r cos theta upon r square minus 2z upon r square plus r multiplied by r dz dr d theta. On simplification of this integral, we find finally the value of the integral as 8 root 2 upon 3 minus 4 log 2 minus 4 by 3 pi. Hello viewers, today in this program I have explained some important theorem of vector calculus, namely Green's theorem, Stokes theorem and Gauss divergence theorem. These theorems represent the integral relationship in integration as line integral to surface integral to volume integral. So, if we have the knowledge of evaluating line integral, surface integral and volume integral, we can use this theorem very nicely. The Green's theorem convert the line integral into surface integral if it is given in the xy plane, while in the Stokes theorem we convert line integral into surface integral in space, and the third theorem, the Gauss divergence theorem, convert surface integral into volume integral. Hope you have enjoyed the lecture. Thank you.